The discovery that the universe is expanding. Part A. For most of human history, people believed the universe was eternal, unchanging, and fixed. The stars appeared permanent, arranged in patterns that never altered from generation to generation. Ancient civilizations looked at the night sky and saw stability rather than motion. Philosophers such as Aristotle imagined a cosmos that was perfect and unchanging beyond Earth, while many early astronomers assumed that the universe had always existed in the same form. The idea that the entire universe could grow, evolve, or expand would have sounded impossible for thousands of years. The journey toward discovering an expanding universe began not with cosmology, but with careful observation. Early astronomers relied only on human eyesight, limiting what they could see to a few thousand stars within our own galaxy. The Milky Way was believed to be the entire universe. Faint cloudy patches seen in the sky, known as nebulae, were mysterious objects whose true nature remained unknown. Some scientists thought they were gas clouds inside our galaxy, while others suspected they might be distant systems far beyond it. This debate would eventually lead to one of the greatest scientific revolutions in history. Invention of the telescope dramatically expanded humanity's view of space. Galileo's observations in the 17th century revealed moons orbiting Jupiter and phases of Venus, proving that Earth was not the center of everything. Yet even after these discoveries, scientists still believed the universe itself was static. Isaac Newton's laws of motion and gravity described how objects moved, but they also raised a puzzle. Gravity always attracts. If the universe were filled with matter everywhere, gravitational attraction should pull everything together over time. Why then did the universe not collapse? Physicist Newton himself recognized this problem, but avoided resolving it fully. Later scientists suggested that an infinite universe might balance gravitational forces in every direction, preventing collapse. This idea allowed physicists to imagine a stable, eternal cosmos. For centuries, the assumption of a static universe remained unchallenged because there was no observational evidence suggesting otherwise. The situation began to change in the late 19th and early 20th centuries with improvements in technology and spectroscopy, the study of light. Scientists discovered that light carries information about motion. When an object moves away from an observer, its light stretches toward the red end of the spectrum, a phenomenon known as redshift. When an object moves closer, its light shifts toward blue wavelengths. This principle, based on the Doppler effect, became a powerful tool for measuring cosmic motion. Astronomers started applying spectroscopy to distant nebulae. At first, the results were puzzling. Many nebulae showed strong redshifts, indicating they were moving away from Earth at high speeds. Some scientists initially believed this motion might simply reflect local movement within the Milky Way. However, the velocities measured were extraordinarily large, far greater than typical stellar motions. Something much bigger seemed to be happening. Around the same time, a theoretical breakthrough occurred. In 1915, Albert Einstein introduced the theory of general relativity, fundamentally changing humanity's understanding of gravity. Instead of describing gravity as a force pulling objects together, Einstein explained it as the curvature of spacetime caused by mass and energy. According to this theory, the geometry of the universe itself could evolve over time. When Einstein applied his equations to the entire universe, he encountered an unexpected result. The equations suggested that the universe could not remain static. It should either expand or contract. This conclusion disturbed Einstein because the prevailing belief among scientists favored an unchanging cosmos. To preserve stability, he introduced an additional mathematical term called the cosmological constant, designed to counteract gravity and hold the universe steady. Einstein later reportedly referred to this adjustment as his greatest mistake, though modern physics has given the idea renewed importance. Meanwhile, other physicists explored solutions to Einstein's equations without forcing stability. Russian mathematician Alexander Friedman showed that expanding or contracting universes naturally emerged from general relativity. Belgian priest and physicist Georges Lemaitre independently reached a similar conclusion and proposed that the universe began from a dense initial state and has been expanding ever since. At the time, these ideas were largely theoretical and lacked strong observational proof. The decisive evidence arrived through astronomical observation. Edwin Hubble, working at the Mount Wilson Observatory in California during the 1920s, used one of the world's most powerful telescopes to study distant nebulae. Hubble identified special types of stars called Cepheid variables whose brightness changes in a predictable way. By measuring their brightness, astronomers could determine their distance from Earth with remarkable accuracy. Hubble's measurements revealed something astonishing. Many nebulae were far outside the Milky Way, meaning they were separate galaxies containing billions of stars. The universe suddenly became vastly larger than anyone had imagined. But Hubble's most important discovery came when he compared galaxy distances with their redshifts. He found a clear pattern. The farther away a galaxy was, the faster it appeared to move away from us. This relationship became known as Hubble's law. It did not suggest that Earth occupied a special central position. Instead, it implied that expansion occurs uniformly everywhere. Any observer in any galaxy would see other galaxies moving away in the same manner. This observation transformed cosmology. Rather than galaxies flying through pre-existing empty space, scientists realized that space itself must be expanding. Distances between galaxies increase because the underlying fabric of space-time stretches. The universe behaves not like an explosion, sending fragments outward into emptiness, but like a growing geometric structure. Understanding this idea required abandoning everyday intuition. In ordinary experience, expansion always occurs within something larger. A gas expands into a container, a ripple spreads across water. However, cosmic expansion differs fundamentally because space is not an object inside another environment. Space defines distance itself. When space expands, the scale used to measure separation changes. Early reactions to Hubble's discovery were mixed. Some scientists resisted the idea because it implied a dynamic universe with a beginning in time, which seemed philosophically uncomfortable. Others questioned whether redshift truly indicated motion. Alternative explanations were proposed, including theories suggesting light might lose energy over vast distances. Over time, however, accumulating evidence supported expansion more strongly than any competing explanation. One reason the discovery was so revolutionary is that it shifted cosmology from philosophy to observational science. For centuries, questions about the universe's origin belonged mainly to metaphysics. With Hubble's data, cosmology became measurable. Scientists could estimate the universe's age by calculating how long expansion had been occurring. If galaxies are moving apart today, then in the past they must have been closer together. This realization led naturally to the concept later called the Big Bang. The term does not describe an explosion in space, but rather the expansion of space from an extremely hot, dense early state. As scientists traced cosmic expansion backward in time, they concluded that the universe was once smaller, hotter, and more uniform. Another crucial aspect of the discovery was understanding that expansion occurs everywhere simultaneously. There is no unique center. This idea can feel counterintuitive because explosions in everyday life always have centers. Yet in cosmic expansio, every region moves away from every other region because the metric of space changes uniformly. Astronomers confirmed expansion using multiple independent methods. Measurements of galaxy distributions, cosmic background radiation, and later observations of distant supernovae all supported the expanding universe model. Each new line of evidence strengthened confidence that expansion was not an illusion or measurement error, but a fundamental property of reality. The discovery also reshaped humanity's philosophical perspective. A changing universe implies cosmic history. Stars form and die. Galaxies evolve, and conditions change over billions of years. The universe became a story unfolding through time rather than a static stage. Richard Feynman often emphasized that scientific discoveries frequently overturn deeply held assumptions. The expanding universe is a perfect example. What seemed obvious, that the cosmos must be fixed, turned out to be wrong once better measurements became available. Science advanced not through certainty, but through questioning and observation. Importantly, Expansion does not mean everything grows larger. Atoms, planets, and galaxies remain bound by forces strong enough to resist expansion. Only on immense intergalactic scales does the stretching of space-time dominate. This distinction helped scientists reconcile cosmic expansion with the stability of everyday objects. As observations improved throughout the 20th century, astronomers measured expansion more precisely. The rate of expansion, known as the Hubble constant, became one of the most important numbers in cosmology. Determining its exact value remains an active area of research even today, as different measurement methods produce slightly different results. The discovery that the universe expands marked a turning point comparable to recognizing Earth orbits the Sun. Humanity moved from viewing itself within a timeless cosmos to understanding that the universe has a dynamic past and evolving future. Expansion suggests that cosmic conditions were once radically different and will continue to change. This transformation and understanding did not happen overnight. It required decades of theoretical work, technological advancement, and careful verification. Scientists learned that the universe itself could behave according to mathematical laws governing space-time geometry. Expansion emerged not as speculation, but as an unavoidable conclusion drawn from evidence. By the mid-20th century, the expanding universe became the foundation of modern cosmology. Researchers began exploring deeper questions. What caused expansion? Will it continue forever? Does the universe have a boundary? And perhaps most intriguingly, if space is expanding, what does that really mean? And about reality itself. By the discovery of expansion opened the door to these profound questions. It changed how humanity understands existence, time, and cosmic origins. Instead of living in a static universe that simply exists, we inhabit a cosmos in motion, continuously evolving on scales almost beyond imagination. This realization represents one of the greatest intellectual achievements in human history. Through observation, mathematics, and curiosity, scientists uncovered evidence that the universe itself is dynamic. The night sky, once seen as eternal and unchanging, became a snapshot of an ongoing cosmic transformation. And this discovery, born from faint spectral lines, careful measurements, and bold theoretical thinking, set the stage for everything modern cosmology seeks to understand today. The expanding universe is not just a scientific fact. It is the starting point for exploring our cosmic past, present, and future. Recognition that the universe is expanding did not end scientific inquiry. Instead, it opened an entirely new era of questions and discoveries. Once astronomers accepted that galaxies are moving apart because space itself stretches, the next challenge was understanding how this expansion behaves over time and what it reveals about the history of the cosmos. The discovery transformed astronomy into cosmology, the scientific study of the universe as a whole. After Edwin Hubble established the relationship between distance and recession speed, scientists began refining measurements. Early calculations suggested the universe was surprisingly young, younger even than Earth, according to geological estimates. This contradiction revealed that measurements were still imperfect. Astronomers improved their techniques, recalibrated cosmic distance scales, and discovered that earlier data underestimated distances to galaxies. As accuracy improved, the estimated age of the universe increased, eventually aligning with evidence from stellar evolution and radioactive dating. The expanding universe implied something profound. If galaxies are moving apart today, then in the distant past, everything must have been closer together. Running cosmic history backward leads to a state where matter and energy were compressed into extremely high density and temperature. This idea gradually developed into the modern Big Bang theory. Importantly, the Big Bang does not describe an explosion occurring at a particular location. Instead, it represents the expansion of space everywhere simultaneously from an earlier dense condition. During the mid-20th century, scientists debated competing cosmological models. One alternative was the steady-state theory, which proposed that the universe expands but remains essentially unchanged because new matter C, continuously forms to maintain constant density. This model preserved the philosophical idea of an eternal universe without a beginning. For a time, both expanding Big Bang models and steady-state models were taken seriously because observational evidence was still limited. The decisive turning point came in 1965 with the accidental discovery of the cosmic microwave background radiation. Two researchers, Arno Penzias and Robert Wilson, detected faint microwave noise coming uniformly from every direction in space. This radiation turned out to be leftover heat from an early hot phase of the universe. Its existence strongly supported the idea that the universe began in a dense, hot state and has been expanding and cooling ever since. The expanding universe was no longer just inferred from galaxy motion. It now had thermal evidence imprinted across the sky. As expansion continued to be studied, scientists realized that galaxies are not actually traveling through space away from a central explosion. Instead, the distances between galaxies increase as space-time itself evolves. This distinction is essential. In ordinary motion, objects move through space from one location to another. In cosmic expansion, the coordinates defining distance stretch, so separation increases even if galaxies remain locally at rest relative to nearby space. To understand this more deeply, physicists turned again to general relativity. Einstein's equations showed that the universe's expansion depends on its total energy content, matter radiation, and other forms of energy. Gravity from matter tends to slow expansion, pulling galaxies toward each other. Therefore, for decades, scientists expected expansion to gradually decelerate over time. Astronomers began searching for evidence of this slowing. By observing extremely distant supernova explosions, researchers could measure how expansion behaved billions of years ago. These exploding stars act as cosmic distance markers because their brightness follows predictable patterns. In the late 90s, two independent research teams made a startling discovery. Distant supernovae appeared dimmer than expected, meaning they were farther away than predicted by a slowing universe. The conclusion shocked the scientific community. Expansion was not slowing down, it was accelerating. Something unknown was pushing space to expand faster over time. Scientists named this mysterious influence dark energy. Although its exact nature remains unknown, dark energy appears to make up most of the universe's total energy content. This discovery reshaped understanding of cosmic expansion once again. Instead of gravity gradually halting expansion, the universe may continue expanding indefinitely, growing colder and emptier as galaxies drift farther apart. Over immense timescales, distant galaxies could move beyond the observable horizon, becoming permanently invisible because light from them would never reach us. Another important realization connected expansion with cosmic structure. Although space expands on large scales, smaller systems resist expansion due to stronger forces. Gravity binds galaxies together, electromagnetic forces hold atoms intact, and nuclear forces stabilize atomic nuclei. Expansion becomes noticeable only across vast intergalactic distances where gravitational attraction is weak. This explains why everyday objects do not grow larger, despite cosmic expansion occurring everywhere. Scientists also investigated whether expansion implies an edge to the universe. Observations show no evidence of a boundary. The universe appears homogeneous and isotropic on large scales, meaning it looks roughly the same in every direction. Expansion does not create an outer frontier where space pushes into emptiness. Instead, new distance emerges uniformly throughout space-time. This idea challenges ordinary thinking because humans naturally imagine expansion requiring an external environment. Richard Feynman often emphasized that misunderstanding arises when familiar language is applied beyond its proper domain. Words like outside or center may not apply to the universe as a whole. The expanding universe does not require a surrounding space. Expansion is simply a change in geometry. As measurements improved, astronomers mapped large-scale cosmic structures, clusters, filaments, and vast voids spanning hundreds of millions of light years. These structures formed from tiny density variations present in the early universe. Expansion played a crucial role. by allowing matter to spread and evolve under gravity, eventually forming galaxies and stars. Without expansion, cosmic structure as we know it would not exist. The discovery of expansion also allowed scientists to estimate cosmic timelines. By measuring how fast the universe expands today and understanding how expansion changes, researchers can calculate when stars first formed, when galaxies assembled, and how long the universe has existed. Current estimates place its age at about 13.8 billion years. This number emerges directly from understanding expansion. Another remarkable consequence involves cosmic horizons. Because expansion stretches space, there are regions so distant that light emitted today will never reach us. The observable universe represents only the portion from which light has had time to arrive since cosmic expansion began. Beyond that lies more universe, potentially infinite, forever beyond observation. Modern cosmology continues refining XPAS and ion measurements with advanced telescopes and satellites, observations of galaxy clustering, gravitational lensing, and background radiation all contribute to understanding how expansion evolved. Interestingly, different measurement techniques produce slightly different values for the expansion rate, creating what scientists call the Hubble tension. This discrepancy may hint at new physics yet to be discovered. The expanding universe also influences fundamental philosophical questions. If the universe evolves, then conditions allowing life emerge gradually rather than existing eternally. Stars forged heavy elements through nuclear fusion, later dispersing them through supernova explosions. Expansion created the environment in which galaxies formed and planetary systems developed. In a sense, cosmic expansion helped make life possible by shaping the universe structure over billions of years. Feynman admired discoveries that forced humans to rethink assumptions. The expanding universe teaches that reality may not conform to intuitive expectations. Instead of a static cosmic backdrop, the universe behaves dynamically, governed by mathematical laws that describe space-time itself. Expansion reveals that even emptiness is active, capable of changing and influencing cosmic destiny. Scientists now explore deeper questions arising from expansion. Did expansion begin from a quantum event? Could multiple universes exist with different expansion histories? Will acceleration continue forever, or might unknown physics alter the universe's fate? Each question traces back to the original discovery that galaxies move apart. Future observatories aim to measure expansion with unprecedented precision. By studying gravitational waves, mapping billions of galaxies, and analyzing ancient light, researchers hope to uncover the true nature of dark energy and refine understanding of cosmic evolution. The discovery made nearly a century ago remains at the center of modern astrophysics. Looking back, the discovery that the universe expands represents a triumph of human curiosity. It required combining theory and observation, challenging tradition and accepting results that contradicted intuition. From faint spectral lines in distant galaxies emerged a new vision of reality, a universe not frozen in time, but unfolding continuously. Today, when we observe distant galaxies through powerful telescopes, we are not simply seeing remote objects, we are witnessing expansion itself, the stretching of space-time carrying light across billions of years to reach us. Every photon arriving from deep space carries evidence that the universe is larger now than when that light began its journey. The discovery of expansion changed humanity's cosmic perspective forever. It revealed that the universe has a history, a direction of change, and possibly a future shaped by forces still not fully understood. What began as a puzzling observation of redshift became one of the deepest insights into existence itself. Thus, the expanding universe stands as one of science's greatest achievements, proof that through observation, mathematics, and persistence, humanity can uncover truths about the largest possible scale of reality. The cosmos is not static, it grows, evolves, and transforms, and our understanding continues to expand along with it. When people first hear that the universe is expanding, they often imagine galaxies rushing outward into empty space like fragments from an explosion. This image feels natural because it matches everyday experience. When a bomb explodes, debris flies outward into surrounding air. When a balloon inflates, it grows larger inside a room. Our intuition tells us expansion always means objects moving into something else. However, in physics, cosmic expansion means something very different. Understanding what expansion truly means requires changing how we think about space, motion, and even reality itself. To begin, we must separate two ideas that are often confused: motion through space and expansion of space. In ordinary motion, an object travels from one place to another while space itself remains unchanged. A car drives along a bay, road. A planet orbits a star. A rocket travels between planets. In all these cases, space acts as a stage where motion occurs. Distances between fixed points remain constant unless objects physically move. Cosmic expansion, however, involves the stage itself changing. Instead of galaxies moving through space away from a central point, the distances between galaxies increase because the geometry of space evolves over time. Space itself stretches. This is not just poetic language, it is a precise physical description supported by Einstein's theory of general relativity. Before Einstein, space and time were treated as separate and absolute. According to Newtonian physics, space existed as an unchanging three-dimensional grid extending infinitely in all directions. Time flowed uniformly everywhere. Objects moved within this fixed background, but the background itself never changed. Under this framework, the idea of expanding space would make little sense because space was assumed to be permanent and static. Einstein's work transformed this picture completely. General relativity introduced the concept of space-time, a unified structure combining space and time into a single dynamic entity. Instead of gravity being a force pulling objects together, massive objects curve space-time and objects move along paths determined by that curvature. Planets orbit stars because space-time around the star is curved, not because an invisible force pulls them in the traditional sense. One of the most revolutionary consequences of general relativity is that space-time itself can change. It can bend, stretch, ripple, and evolve. The universe is not embedded within space-time as an object inside a container. Rather, space-time is the universe structure. Therefore, when physicists say the universe expands, they mean space-time itself changes scale. To understand this idea more clearly, physicists use mathematical descriptions called metrics. A metric defines how distances are measured between points. In an expanding universe, the metric changes over time, meaning the measured distance between two stationary galaxies increases even though neither galaxy moves locally through space. Imagine placing dots on a rubber sheet. If the sheet stretches uniformly, every dot moves farther away from every other dot, even though none of the dots slide across the surface. The increase in separation results entirely from the stretching of the surface itself. This analogy captures the essence of cosmic expansion, although the real universe involves three spatial dimensions rather than two. An important consequence follows from this. There is no special center of expansion. In an ordinary explosion, all motion originates from a central location. But when space expands uniformly, every observer sees distant galaxies moving away. Observers in any galaxy would measure the same large-scale expansion. This property aligns perfectly with observations showing no preferred direction or central position in the universe. Another key aspect of expansion involves scale. Expansion operates primarily across vast cosmic distances. On smaller scales, other forces dominate. Gravity binds galaxies together. Electromagnetic forces hold atoms intact, and strong nuclear forces stabilize atomic nuclei. These forces are far stronger than the gentle stretching effect of cosmic expansion. As a result, planets, stars, and even galaxies do not expand along with the universe. This distinction often surprises people. If space expands everywhere, why does Earth not grow larger? The answer lies in competing forces. Expansion affects regions where gravitational binding is weak, Inside galaxies or solar systems, gravity overpowers expansion, preventing local stretching. Cosmic expansion becomes noticeable only between large galaxy clusters, separated by immense empty regions. To measure expansion, astronomers rely on light. As space expands, wavelengths of light traveling through it also stretch. This process produces redshift, where light shifts toward longer wavelengths. Unlike the Doppler effect caused by motion through space, cosmological redshift arises because space itself expands while light travels. Each wave of light stretches along with spacetime, increasing its wavelength. This distinction is subtle but crucial. In Doppler redshift, an object moves away through space. In cosmological redshift, space expands between source and observer. Observationally, both effects produce similar results, but their physical meanings differ profoundly. Cosmological redshift provides direct evidence that expansion involves space-time itself, rather than simple motion. Another surprising consequence is that galaxies can appear to recede faster than the speed of light without violating relativity. Special relativity limits how fast objects can move through space relative to nearby observers. However, it does not limit how quickly space itself can expand. Over extremely large distances, expansion can increase separation faster than light travels because no object locally breaks the speed limit. This leads to the concept of the observable universe. Light from extremely distant regions may never reach us because expansion increases distance faster than light can bridge it. Those regions still exist but remain permanently beyond observation. Expansion therefore shapes not only cosmic structure but also the limits of knowledge itself. Mathematically, expansion is described using a quantity called the scale factor. The scale factor represents how distances in the universe change W, ith time. When the scale factor increases, the universe expands. When it decreases, the universe consents. When it decreases, the universe contracts. Cosmologists use this parameter to model cosmic history, tracing how expansion evolved from the early universe to the present day. In the early universe, expansion occurred rapidly. Shortly after the universe began, a brief period known as cosmic inflation may have caused space to expand exponentially fast. During inflation, tiny quantum fluctuations were stretched to cosmic scales, eventually forming the seeds of galaxies. This idea explains why the universe appears remarkably uniform on large scales. After inflation ended, expansion continued but slowed due to gravitational attraction from matter. Billions of years later, dark energy began dominating cosmic dynamics, causing expansion to accelerate again. This changing rate shows that expansion is not constant. It depends on the energy content of the universe. Understanding expansion also changes how we interpret cosmic time. Because light takes time to travel, observing distant galaxies means looking into the past. The farther away an object is, the earlier in cosmic history we see it. Expansion stretches light during its journey, encoding information about how much the universe has grown since that light was emitted. One might ask whether expansion means new space is being created. In a sense, yes, but not like math, Ariel appearing inside a container. Instead, the geometry describing distances changes continuously. Space does not consist of tiny pieces being added. Rather, the relationships defining separation evolve smoothly according to physical laws. This idea challenges ordinary language. Words like stretching or growing suggest physical substances, yet space-time is not a material object. It is a geometric framework governed by equations of general relativity. Expansion reflects changing geometry rather than mechanical stretching of a substance. Another common misunderstanding is imagining galaxies resisting expansion, like objects pushing against a force. In reality, galaxies simply follow the natural geometry of space-time. They move along paths called geodesics, the equivalent of straight lines in curved space-time. Expansion occurs because these geodesics diverge over time. Richard Feynman often stressed that physics becomes clearer when we rely on precise definitions rather than everyday intuition. The expanding universe forces us to accept that space is dynamic, not passive. It participates actively in cosmic evolution. The discovery that expansion refers to spacetime itself marked a profound shift in scientific thinking. Space is no longer merely emptiness separating objects. It possesses structure, behavior, and history. Distances between galaxies change not because galaxies choose to move apart, but because the universe's geometry evolves. As scientists developed this understanding, they realized expansion connects deeply with fundamental physics. The fate of the universe, whether it expands forever, slows, or changes behavior, depends on energy density, dark energy, and the laws governing space-time. Expansion, therefore, becomes a central concept linking cosmology, gravity, and particle physics. In summary, what expansion means in physics is far more subtle than ordinary expansion. It describes the changing geometry of space-time itself. Galaxies separate because space grows between them, light stretches as it travels, and cosmic history unfolds through evolving distances. The universe is not expanding into something else. Expansion is an intrinsic property of space-time. This realization forms the foundation of modern cosmology. By understanding expansion correctly, scientists gained a framework for explaining observations ranging from galaxy motion to background radiation. The concept redefined humanity's understanding of space, transforming it from a static backdrop into an active participant in cosmic evolution. Understanding that expansion refers to the stretching of space-time rather than motion through space leads naturally to deeper questions. If space itself expands, how does this process affect energy, matter, light, and the long-term fate of the universe? The second half of this explanation explores how physicists interpret expansion mathematically, observationally, and conceptually, revealing why this idea remains one of the most profound insights in modern science. One of the first challenges physicists faced was describing expansion quantitatively. Point observations showed galaxies moving away from one another, but scientists needed a framework explaining how distances change consistently across the universe. General relativity provided this framework through solutions that describe a homogeneous and isotropic cosmos, meaning the universe looks roughly the same everywhere and in every direction when viewed on very large scales. Within this framework, expansion is expressed using the cosmic scale factor, mathematical function representing how distances evolve over time. If two galaxies are separated by a certain distance today, their earlier separation can be calculated by dividing that distance by the scale factor at an earlier moment. This simple idea allows cosmologists to reconstruct cosmic history, tracking how the universe grew from a dense early state into its present vastness. An important implication emerges from this description. Expansion does not require galaxies to possess initial outward velocities. Instead, increasing separation arises naturally from changing geometry. Galaxies follow the structure of space-time itself. They are not pushed outward by an explosion. They simply remain at rest relative to their local space while the space between them expands. This perspective resolves a common misunderstanding. Many imagine expansion as matter flying outward into emptiness, implying a boundary or edge somewhere, beyond the universe. Physics, however, finds no observational evidence of such an edge. Expansion occurs everywhere simultaneously, meaning every region grows relative to every other region. There is no outer surface where expansion meets something else. Another important question concerns energy conservation. In everyday physics, energy is conserved within closed systems. Yet in an expanding universe, light loses energy as its wavelength stretches. Photons traveling through expanding space become redshifted, lowering their energy. Where does this energy go? The answer reveals a subtle aspect of general relativity. Global energy conservation does not operate in the same way on cosmic scales. Because space-time itself evolves, defining total energy for the entire universe becomes complex and sometimes impossible. Energy conservation remains valid locally, but globally the concept must be treated differently. Expansion also influences temperature. In the early universe, matter and radiation were extremely hot because everything was compressed into a smaller volume. As space expanded, radiation wavelengths stretched and temperatures dropped. This cooling allowed particles to combine into atoms, atoms to form gas clouds, and eventually stars and galaxies to emerge. The cosmic microwave background radiation observed today is cooled remnant light from when the universe first began. Transparent, its current temperature reflects billions of years of expansion. Another fascinating consequence involves horizons in the universe. Because expansion stretches space, there are limits to what we can observe. Light travels at a finite speed, and expansion can increase distances faster than light can cross them. As a result, there exist regions whose light will never reach us, even given infinite time. These cosmic horizons define the observable universe, separating what we can potentially see from what remains forever beyond observation. Expansion also reshapes how velocity is interpreted in cosmology. When astronomers say distant galaxies recede at enormous speeds, sometimes exceeding the speed of light, this does not violate relativity. The speed limit applies only to motion through local space. Expansion increases distances because space itself grows, allowing effective recession speeds greater than light without breaking physical laws. This distinction highlights the difference between local physics and global cosmology. Locally, physics behaves according to familiar rules. Experiments on Earth or within our galaxy show no direct evidence of expansion because local forces dominate. Globally, however, space-time evolves according to large-scale energy distribution. The same universe contains both stable local environments and expanding cosmic structure simultaneously. The role of gravity in expansion adds further complexity. Gravity attracts matter, working against expansion. Early in cosmic history, when matter density was high, gravity slowed expansion significantly. Scientists once expected gravity might eventually halt expansion entirely, possibly leading to a future contraction known as the Big Crunch. However, observations of accelerating expansion revealed that another component, dark energy, now dominates cosmic dynamics. Dark energy behaves differently from matter and radiation. Instead of slowing expansion, it appears to drive space-time apart more rapidly. One interpretation links dark energy to vacuum energy, an intrinsic energy associated with empty space itself. If empty space possesses energy, then as expansion creates more space, the total dark energy increases, accelerating expansion further. This idea shows again that space is not merely emptiness, but an active participant in cosmic evolution. Expansion also affects how structures form. In the early universe, tiny density variations existed, regions slightly denser than average. Gravity amplified these differences over time, pulling matter together to form galaxies and clusters. Expansion prevented all matter from collapsing into a single massive structure by continually increasing distances. The balance between gravitational attraction and expansion shaped the large-scale structure observed today. Another subtle effect involves time itself. Because space-time combines space and time, expansion influences how cosmic time is measured. Observers moving with cosmic expansion share a common cosmic clock, allowing scientists to define a universal timeline beginning from the early hot phase of the universe. This shared cosmic time enables comparison between distant observations and theoretical models. As measurements improved, astronomers discovered that expansion history encodes information about fundamental physics. By studying how expansion changed over billions of years, scientists infer properties of dark matter, dark energy, and even neutrinos. Expansion becomes a laboratory for testing physical laws under conditions impossible to recreate on Earth. Modern observations rely on several independent techniques. Supernova explosions measure distances across vast scales. Patterns in cosmic background radiation reveal early expansion conditions. Large galaxy surveys map how structure evolved as expansion progressed. Gravitational lensing shows how matter distribution interacts with expanding spacetime. Together, these methods create a consistent picture, confirming that expansion reflects changing geometry rather than simple motion. Philosophically, understanding expansion forces reconsideration of what space truly is. Instead of being a passive emptiness, space behaves more like a dynamic entity with measurable properties. It can expand, carry energy, influence motion, and shape cosmic destiny. This realization represents one of the deepest conceptual shifts in physics since the scientific revolution. Richard Feynman frequently emphasized that nature does not conform to human expectations, shaped by everyday experience. Expansion exemplifies this lesson. The universe operates according to mathematical principles that may feel unfamiliar yet produce precise, testable predictions. Accepting expansion required abandoning intuitive ideas about absolute space and embracing a more abstract but accurate understanding. Another interesting implication concerns the future. If expansion continues accelerating, distant galaxies will gradually disappear from view as their light becomes too stretched to detect. Far future observers might see only their local galaxy group, unaware of the broader universe. Expansion, therefore, not only shapes cosmic history but also determines what future civilizations can know about the cosmos. Scientists also explore whether expansion could change in unexpected ways. Some theories suggest dark energy might vary over time. Others propose modifications to gravity itself. Precise measurements of expansion aim to distinguish between these possibilities, potentially revealing new physics beyond current theories. Despite its complexity, the concept of expansion rests on simple observational facts. Galaxies appear redshifted, distant regions grow farther apart, and cosmic radiation cools over time. From these clues emerges a coherent picture of a dynamic universe governed by evolving space-time geometry. Ultimately, understanding what expansion nets in physics transforms our perception of reality. Distance is not fixed, it evolves. Space is not static, it evolves. Space is not static, it changes. The universe is not merely a collection of objects, but a dynamic structure whose geometry unfolds through time. The expansion of the universe teaches that even the most fundamental aspects of existence, space and time themselves, are part of an ongoing process. Rather than asking what objects move within the universe, physics invites us to see the universe itself as something that grows and evolves. This insight stands as one of humanity's greatest intellectual achievements. By observing faint light from distant galaxies and applying mathematical reasoning, scientists uncovered the true meaning of cosmic expansion, not motion into emptiness, but the continuous transformation of space-time itself. One of the most fascinating and often misunderstood ideas in modern cosmology is why galaxies appear to move away from one another, even though they are not actually traveling through space in the ordinary sense. At first glance, observations seem straightforward. Telescopes show distant galaxies receding, their light shifted toward the red end of the spectrum. This looks similar to how a passing ambulance siren changes pitch as it moves away. Naturally, many people assume galaxies are simply flying outward into empty space after a cosmic explosion. However, physics reveals a far deeper explanation. Galaxies separate, not because they are moving through space, but because space itself expands between them. To understand this concept, we must first reconsider what motion means. In everyday life, motion involves an object changing position relative to its surroundings. A car drives along a road, an airplane crosses the sky, or a planet orbits a star. In all these examples, space remains fixed while objects move inside it. The background does not change, only the objects do. Cosmic expansion works differently. According to Einstein's theory of general relativity, space is not a static stage. Instead, space and time form a unified structure called space-time, which can stretch and evolve. When scientists say the universe expands, they mean the distances defined by space-time increase over time. Galaxies are not racing through space, they are being carried apart as the fabric of space-time itself grows. A useful way to visualize this idea is to imagine points drawn on a flexible surface. If the surface stretches evenly, every point becomes farther from every other point, even though none of the points slide across the surface. Each point stays locally still, yet the distances between them increase. Similarly, galaxies remain mostly stationary relative to their local surroundings, while expansion increases the space separating them. This explanation resolves an important puzzle. Why does every galaxy appear to move away from us? If galaxies were flying outward from a single explosion, observers near the center would see others receding, but observers elsewhere would see uneven motion. Instead, observations show that expansion looks the same from any galaxy. Every observer sees distant galaxies moving away in all directions. This uniformity makes sense only if space itself expands everywhere at once. The relationship between distance and recession speed further supports this idea. Astronomers discovered that more distant galaxies recede faster than nearby ones. This pattern, known as Hubble's law, arises naturally from expanding space. If space stretches uniformly, then larger distances grow more quickly, simply because there is more space between objects to expand. No special force pushes galaxies outward. Separation increases as a property of geometry. Another important aspect involves cosmological redshift. Light traveling through expanding space stretches along with space-time. As wavelengths lengthen, light shifts toward red colors. This redshift is not merely caused by galaxies moving through space like speeding objects. Instead, the light itself expands during its journey across the universe. Each wave becomes longer because the space it occupies grows over time. Observing this effect provides direct evidence that expansion affects space-time itself. One might wonder whether galaxies feel a force pulling them apart. Surprisingly, they do not. Expansion is not like wind pushing objects away from each other. Galaxies follow natural paths through space-time called geodesics, which represent the straightest possible motion in curved geometry. Because space-time evolves, these paths gradually diverge, increasing separation without requiring a physical push. This also explains why galaxies remain intact despite expansion. Inside galaxies, gravity strongly binds stars together. On smaller scales, electromagnetic forces hold atoms and molecules in place. These forces are far stronger than the gentle effect of cosmic expansion. As a result, solar systems, planets, and even galaxy clusters do not expand significantly. Expansion becomes noticeable only across immense distances where gravitational binding is weak. An especially surprising consequence is that extremely distant galaxies can appear to recede faster than the speed of light. At first, this seems to violate Einstein's relativity, which states that nothing can move faster than light. The key detail is that the speed limit applies to motion through local space, not to the expansion of space itself. When space-time expands, distances can increase faster than light can travel without breaking physical laws, because no object locally exceeds light speed. This phenomenon leads to cosmic horizons. Some galaxies are so distant that expansion carries them away faster than their light can reach us. Even light emitted today from those regions will never arrive. They are not disappearing physically. Rather, expanding space prevents signals from bridging the growing distance. This shows how expansion shapes not only motion, but also what parts of the universe are observable. The idea that galaxies move apart without traveling through space challenges human intuition because everyday experience never involves expanding geometry. Our brains evolved to understand motion within fixed environments, not environments that change scale. Richard Feynman often emphasized that physics becomes difficult when we rely too heavily on common sense formed from limited experience. The universe operates according to rules that sometimes lie beyond direct intuition. Another way to understand the concept is to imagine measuring distances with a ruler that gradually grows longer. If the ruler expands while objects remain unchanged, measured distances increase even though objects have not moved. In cosmic expansion, space-time itself acts like that changing ruler. The definition of distance evolves, creating the appearance of motion. This perspective eliminates the need for a central explosion or a special location in the universe. Expansion has no center within space because every region expands equally. Each galaxy sees itself surrounded by others moving away. The universe does not expand from a point into emptiness. Rather, all of space grows simultaneously. Understanding why galaxies separate without traveling through space represents one of the greatest conceptual breakthroughs in science. It transforms expansion from a simple motion problem into a geometric property of spacetime. Galaxies are passengers carried by the evolution of the universe's structure rather than travelers speeding through a pre-existing void. Ultimately, this idea reveals something profound about reality. Space is not empty nothingness, but an active component of the cosmos. Its geometry changes, influencing how matter moves and how light travels. The apparent motion of galaxies is therefore a reflection of cosmic evolution itself, a sign that the universe is dynamic, continuously changing, and far more subtle than everyday experience suggests. To understand cosmic expansion properly, one must understand the concept of space-time, because expansion is not simply about galaxies moving apart, it is about space-time itself changing. The idea of space-time represents one of the most revolutionary developments in physics, transforming how scientists understand gravity, motion, and the evolution of the universe. Without space-time, the expanding universe would make little sense. Before the 20th century, scientists believed space and time were separate and absolute. Space was thought to be a fixed, invisible stage, extending endlessly in all directions, while time flowed uniformly for everyone, everywhere. Objects moved through space as time passed, but space itself never changed. This view came largely from Isaac Newton's physics, which worked extremely well for everyday motion in planetary orbits. However, deeper observations of nature eventually revealed limitations in this classical picture. Albert Einstein changed this understanding through his theories of relativity. First, special relativity showed that space and time are connected. Measurements of distance and time depend on the observer's motion. Events that appear simultaneous to one observer may not be simultaneous to another. This discovery suggested that space and time were not independent entities, but parts of a unified structure. Einstein's general theory of relativity extended this idea further by describing gravity not as a force, but as curvature in space-time. Massive objects such as stars and galaxies bend space-time around them. Objects moving nearby follow curved paths because the geometry through which they travel is curved. A planet orbits a star not because it is pulled by an invisible force in the traditional sense, but because it moves along the natural paths shaped by curved space-time. This insight introduced a powerful new concept. Space-time is dynamic. It can stretch, bend, ripple, and evolve. It is not merely a background where events happen. It participates actively in physical processes. Cosmic expansion is one of the most dramatic examples of this dynamism. In cosmology, space-time provides the framework that defines distance between galaxies. When scientists measure how far apart galaxies are, they are measuring distances within space-time. If space-time changes, distances change automatically, even if galaxies themselves remain locally at rest. Therefore, expansion means space-time's geometry evolves over time, increasing separation between distant regions. One key feature of space-time expansion is uniformity. Observations show that on large scales, the universe appears nearly the same in all directions. This property allows cosmologists to describe the universe using models where time expands evenly everywhere. Instead of objects flying outward from a central location, every region of space-time grows simultaneously. This explains why observers in any galaxy see others moving away from them. The mathematical description of this process comes from solutions to Einstein's equations, known as cosmological models. These solutions show that space-time can expand or contract depending on the energy and matter it contains. Matter and radiation influence how space-time evolves because energy determines curvature. The universe's expansion rate, therefore, reflects its total energy content. An important consequence of space-time expansion involves light. Light always travels at a constant speed locally, but the distance it must cross can grow while it travels. As space-time expands, light waves stretch along with it. This stretching increases their wavelength, producing cosmological redshift. Observing redshift allows astronomers to measure how much space-time has expanded since the light was emitted. Space-time also determines cosmic time. Because expansion occurs uniformly, scientists can define a shared cosmic clock for observers moving with the expansion of the universe. This allows researchers to describe events such as galaxy formation, star birth, and cosmic cooling within a consistent timeline. The age of the universe itself is calculated by studying how spacetime has expanded over billions of years. Another crucial role of space-time is explaining why expansion does not affect everything equally. Locally, space-time can curve strongly around massive objects. Within galaxies, gravitational curvature dominates over cosmic expansion. Stars remain bound to galaxies because local space-time geometry prevents expansion from pulling them apart. In contrast, between distant galaxies where matter density is low, space-time expansion becomes noticeable. This balance between local curvature and global expansion highlights the flexibility of space-time. It behaves differently depending on scale. On small scales, gravity shapes space-time into stable structures. On large scales, the overall geometry evolves, causing cosmic expansion. Both behaviors arise from the same underlying physical laws. Space-time expansion also connects directly to one of the biggest mysteries in modern physics: dark energy. Observations show that expansion is accelerating, meaning space-time stretches faster over time. Dark energy appears to be a property of space-time itself, exerting a repulsive gravitational effect. If empty space contains energy, then as space-time expands and more space exists, the influence of dark energy grows stronger, driving further expansion. This idea reveals something extraordinary. Emptiness is not truly empty. Even regions with no matter still, P, possess space-time structure and energy. Expansion demonstrates that vacuum itself has physical significance, influencing the universe's future. Another fascinating role of space-time involves cosmic horizons. Because expansion changes distances, there are limits to how far we can see. Some regions lie beyond our observable universe because space-time expansion prevents their light from ever reaching us. These horizons arise naturally from space-time geometry rather than from physical barriers. Understanding space-time also removes the need to imagine the universe expanding into something else. If space-time defines all measurable distances and directions, then asking what lies outside space-time may not have physical meaning. Expansion occurs within space-time itself, not into an external environment. This idea challenges intuition, but follows directly from relativity. Richard Feynman often emphasized that physics advances when we accept mathematical descriptions, even when they contradict everyday expectations. The role of space-time in cosmic expansion perfectly illustrates this principle. Reality at cosmic scales does not behave like familiar objects, expanding into surrounding space. Instead, the structure of reality itself evolves. Space-time's role extends beyond expansion into shaping cosmic history. In the early universe, space-time expanded rapidly during a period called inflat. Ions, smoothing out irregularities and setting initial conditions for galaxy formation. Later, expansion slowed due to gravity, allowing structures to grow. Today, dark energy accelerates expansion again. Each stage reflects changing space-time dynamics, governed by physical laws. Ultimately, space-time serves as both the arena and the actor in cosmic evolution. It defines distances, governs motion, carries light, and determines the universe's fate. Expansion is not something happening inside space-time. It is something space-time itself does. Recognizing this transforms our understanding of the cosmos. The universe is not a collection of objects sitting in emptiness. It is a dynamic geometry unfolding through time. Galaxies, stars, and observers exist within this evolving structure, carried along by the changing fabric of space-time. The role of space-time in cosmic expansion, therefore, represents one of the deepest insights ever achieved in science. It reveals that the universe is not static, but alive with geometric change, continuously reshaping the distances between everything that exists. Richard Feynman was famous not only for his contributions to physics, but also for his extraordinary ability to explain difficult scientific concepts in simple, understandable ways. His approach to explaining the universe, including ideas like cosmic expansion, focused less on memorizing formulas and more on developing deep understanding through clear thinking, curiosity, and honest questioning. The sixth keynote highlights how Feynman's style helps people grasp complex topics such as the expanding universe. One of Feynman's core principles was that true understanding means being able to explain an idea in plain language. He believed that if a scientist could not describe a concept simply, they probably did not understand it fully themselves. Rather than hiding behind complicated terminology, Feynman broke ideas into familiar experiences and logical steps. When discussing cosmic expansion, he avoided unnecessary technical language and instead focused on the meaning behind the mathematics. Feynman often warned against trusting intuition blindly. Human intuition develops from everyday experiences on Earth, where speeds are slow and gravity behaves predictably. But the universe operates on scales far beyond daily life. According to Feynman, confusion arises when people expect nature to behave according to common sense rather than evidence. He encouraged learners to accept that reality may feel strange but still be true if supported by observation and experiment. Another important aspect of his teaching style was curiosity-driven learning. Feynman believed science begins with asking honest questions, even simple ones. Questions like, what does expansion really mean? Or what is space? Were not childish to him. They were essential. By exploring these questions step by step, he guided people toward deeper insights rather than giving answers to memorize. Feynman also emphasized visual thinking and analogies while carefully explaining their limits. For example, scientists sometimes compare cosmic expansion to dots moving apart on an inflating balloon. Feynman would use such analogies to build intuition, but remind listeners that analogies are only tools, not perfect representations. The goal was understanding relationships, not taking comparisons literally. A defining feature of Feynman's explanations was intellectual honesty. He openly admitted when science did not yet know an answer. Instead of pretending certainty, he highlighted mystery as an exciting part of discovery. In discussing the universe, he would explain what theories describe accurately while acknowledging unanswered questions, such as the true nature of dark energy or what existed at the earliest moments of cosmic history. Feynman also believed learning should feel engaging and enjoyable. His explanations often included humor, storytelling, and surprising perspectives that captured attention. By making science feel alive rather than intimidating, he helped people overcome fear of complex subjects. This approach made abstract ideas like space-time expansion accessible to students and non-scientists alike. Another key element of his method was focusing on fundamental principles rather than memorized facts. Instead of listing equations, he explained why physical laws work the way they do. For cosmic expansion, this meant understanding space-time geometry rather than just remembering observational results. Once the basic principle becomes clear, many complicated details naturally follow. Perhaps most importantly, Feynman encouraged skepticism combined with openness. He advised people not to accept explanations simply because authorities said so, but also not to reject ideas because they seem strange. Evidence and logical reasoning should guide belief. This mindset is essential when studying cosmology, where reality often challenges imagination. In summary, Richard Feynman's way of simplifying complex ideas rests on clarity, curiosity, honesty, and deep conceptual understanding. By focusing on meaning instead of complexity, he showed that even the vast and mysterious expanding universe can be understood step by step. His teaching style reminds us that science is not about making things sound complicated, it is about making the complicated understandable. The discovery that the universe is expanding does not only explain its past, it also provides powerful clues about its future. By studying how expansion works today and how it has changed over time, scientists can predict the long-term fate of the cosmos. The seventh keynote focuses on what cosmic expansion reveals about where the universe may be heading and what this means for galaxies, stars, and existence itself. At first, scientists assumed gravity would gradually slow expansion. Since matter attracts matter, the combined gravitational pull of all galaxies should act like a cosmic brake. For much of the 20th century, astronomers debated whether expansion would eventually stop, leaving the universe balanced, or reverse into a contraction known as the Big Crunch, where everything collapses back together. However, observations in the late 19s changed this expectation dramatically. Measurements of distant supernovae showed that expansion is not slowing, it is accelerating. Galaxies are moving apart faster over time, suggesting the presence of a mysterious component called dark energy. This unknown form of energy appears to fill space itself and produces a repulsive gravitational effect, pushing space-time to expand more rapidly. If acceleration continues, the future universe will look very different from today's cosmos. Over billions of years, distant galaxies will move farther away until their light becomes too stretched and faint to detect. Eventually, observers in our galaxy may see only nearby gravitationally bound systems, while the rest of the universe disappears beyond the observable horizon. The night sky, currently filled with countless galaxies, would gradually grow darker. Expansion also affects star formation. Galaxies form stars by gathering gas through gravitational attraction. As expansion increases distances between galaxies, less material becomes available for new star formation. Over trillions of years, existing stars will burn out, and fewer new stars will replace them. The universe will slowly transition into an era dominated by faint stellar remnants such as white dwarfs, neutron stars, and black holes. In an accelerating universe, space itself becomes increasingly empty and cold. Radiation stretches to longer wavelengths, lowering its energy. Temperatures approach absolute zero as cosmic expansion continues. This scenario is often called the heat death of the universe, not because of destruction by heat, but because energy becomes so evenly spread that no useful processes can occur. Despite this seemingly bleak outcome, expansion also reveals something profound about cosmic stability. Local structures remain intact even as the universe grows larger. Our galaxy and nearby galaxies are gravitationally bound and will likely merge long before cosmic isolation becomes complete. Expansion shapes the large-scale future while local systems continue evolving according to gravity. Scientists also explore alternative possibilities. If dark energy changes strength over time, expansion could behave differently. In one speculative scenario, acceleration might increase dramatically, eventually tearing apart galaxies, stars, and even atoms, a hypothetical event sometimes called the Big Rip. While current evidence does not strongly support this outcome, studying expansion helps scientists test such possibilities. Another important lesson from expansion is that the universe has a direction in time. Because space expands and entropy increases, cosmic history moves forward rather than repeating endlessly. Expansion connects the universe's beginning, present evolution, and future destiny into a single continuous story. Richard Feynman often emphasized that science reveals not only answers but perspective. The expanding universe shows that reality is dynamic on the largest possible scale. The cosmos is not a permanent structure but an evolving system shaped by physical laws over immense timescales. Ultimately, cosmic expansion teaches that the universe's future depends on the properties of space-time itself. By measuring expansion today, scientists read clues about billions or even trillions of years ahead. The same process that carried galaxies apart since the early universe will continue shaping cosmic destiny, reminding us that we live within a universe still unfolding.